Okay. Thank you, Shwanta, and thank you everybody to come to this platform and want to listen to me. So, usually it is allowed to take questions anytime, but I will prefer to take questions at the end of my talk. So, let's start. Today, I'll talk about something called fluid gravity correspondence. I will start with what is the meaning of the fluid gravity correspondence. Then, I will introduce what we are trying to give because it is almost 40 years old subject, and so therefore almost everything is there, but what we are trying to do here I will come at the end. So first come to the two well-known equations, and these are highly nonlinear equations. One is the Navier-Stokes equations. We know it actually gives the dynamics of the fluid in the long wavelength regime, whereas the Einstein's equations are actually the equation which governs the dynamics of the space-time, which a long-range kind of force. These are the two completely distinct equations, and they are highly nonlinear. And to get an exact solutions of them, it's completely almost impossible in various cases. And also, these two equations are, since the solutions are not properly known, so these two equations are not properly understood till now. So now what people are trying to do is that they are trying to see if there is any connection between these two equations, so that being the physics of one equation, one can understand the physics of the other equation. So this is what I call a correspondence between the two equations. Now, so one thing is, first question is there any duality or correspondence between them? And if there is anything, that be interesting, because I already said that one can actually to understand the others. And this is the main focus of the fluid gravity correspondence. So there are some hints which actually came from thesis of Damu. What he did is he project the Einstein's equation on a null surface. So null surface means the normal to that null, that surface is null. Say if L is the null, normal to that surface, then L squared is 0. So what Damu did is he projected the Einstein equation on that null surface. Then he found that this equation looks like Navier-Stokes equation, but not exactly the Navier-Stokes equation. But there are certain difference between the Navier-Stokes equation and the Damu type of equation. One is that the viscosity coefficient came negative for Damu, but for real fluid we don't expect that one. But this is one thing I want to mention, that the Einstein equation projected on the hypersurface, which is null, has a structure similar to Navier-Stokes equation, but not exactly. Then Price and Thorne tried to do one thing. Without taking the exact null surface, they project the Einstein equation little away from the null surface and then took the null limit. So then they found that that is also similar to Damu Navier-Stokes equation. So there is nothing new in that sense. Now, a few years back, the Navier group, they actually gave a new interpretation of this Navier-Stokes equation. What they did is, they showed that if there is a conformal fluid kind of thing, the equation of that conformal fluid can be written as an Einstein equation written on the ADS boundary. So you take a ADS black hole and you write down your Einstein equation at the boundary of the ADS black hole. That is similar to the Navier-Stokes equation. So this is in the context of ADS CFT. Here one can show that looking at the Navier-Stokes equation, one can actually write down the ADS black hole solution. So these are the main, some of the old results we have. And Paddy then told that, okay, since there is a connection between Einstein equation and Navier-Stokes equation, probably uh, looking at the degrees of freedom of the Navier-Stokes equation, the gravity degrees of freedom can be understood. So this is sometimes he called as an emergent paradigm, but I will not go into that detail. I just mentioned this thing. Then another approach is there, which is called timelike cutoff approach. If you look at the other three approaches, one is Damour, another is Price. They are actually either on the null surface or little away from the null surface, and then they took the null surface limit. Whereas Caesar's analysis is completely based on safety correspondence. But what these people, this is actually is there is another author which is who is Strominger. What they told is that, okay, let's don't do this kind of analysis. We take a solution of Einstein equation and try to find out if there is a time-like surface, whether we can say that the Navier-Stokes equation can be written on that surface. So I will explain how he had done that. Before going into that, I have to show some of the notations. I will use small a, b, c. These are for space-time indices. Mu, nu, alpha. These are hypersurface indices on which the fluid will be lying. And the capital ones, I will use like angular coordinates. Here I will call it transverse indices. So before going into that, how the Strominger they actually found the solution, let us see how much restriction they have used. First of all, they took the incompressible Navier-Stokes equation. What does it mean? It means the radius of the velocity profile is 0. Del A VA equals to 0. So they took a incompressible Navier-Stokes equation, and then what they found that this Navier-Stokes equation is scale invariant under the scaling of this kind of under the scaling of this kind of transformation. So if you have a solution of this incompressible Navier-Stokes equation like VAP, then you can have a set of solutions which are scaled by velocity is scaled by epsilon, pressure is scaled by epsilon square, whereas the time and tau is the time, and the angular coordinates or the transverse coordinate they scaled as epsilon square and epsilon respectively. Although this analysis, how this scale invariant is not given in the Strominger's papers, but in our paper we actually showed it explicitly. But the underlying thing is that if you have an incompressible Navier-Stokes equation, it has a set of equations, set of solutions which are connected by this kind of scaling transformation. Then what they did is, looking at this scaling, they took this as this epsilon scaling, they took as a order by order correction. I will come to that, what that is. So before going to that, how the Strominger got the solution. So what he did is, he looked at the ADS-CFT approach. But there, what we did, if you have a thermal conformal fluid, then you take the black hole solutions as a gravity side, because black hole solution has a temperature. So you can say that this temperature corresponds to the temperature of the fluid. So the thermal state is mimicked by the ADS black hole state. Then what they did, they wrote the Einstein equation on radius boundary, and they showed that this can be written in similar to Navier-Stokes equation. Now, if you want to add some corrections to the Navier-Stokes equation, the solution for radius solution, you have to take the gradient response. So this is a kind of approach exists in ADS-CFT. Strominger actually took that idea, but in a different way. What he said that okay, we have this scaling argument that uh, incompressible Navier-Stokes equation is invariant under the scaling. So you find a p plus 2-dimensional solution, which is a bulk solution, and you say that your thermal fluid is living on p plus 1 dimension. This p plus 1 dimensional hypersurface I will take as a timelike hypersurface. So some coordinate, space-like coordinate is constant there. And how do you define this bulk solution? Okay, let us start with the, since we have a thermal fluid, let us start with the Rindler spacetime. Because we know the Rindler spacetime is actually the spacetime for the accelerated frame. An accelerated frame at the quantum level can assign temperature on the Rindler horizon. So he took the Rindler spacetime for the base of the bulk solution, and if there are any corrections, so you add the corrections to the Rindler spacetime by looking at the scaling. You take that epsilon as a very small parameter, and order by order you add to that Rindler spacetime the corrections such that on the hypersurface the Einstein equation gives you the Navier-Stokes equation. And also, of course, your ultimate bulk metric has to be the solution of Einstein equation. So this is the basic idea. Now let us summarize what are the scaling. The scaling is one is VA, goes as order of epsilon, pressure, order of epsilon square, the spatial derivative along the transverse coordinate order of epsilon, along time coordinate it is epsilon square. So start with the base metric, which is Rindler 1. Then we added several terms. This is the order epsilon term, and this is order epsilon square term. So initially you may understand that this is ad hoc. Actually, in his paper, he said that this is my solution. But what I understood is that you allow the order by order terms to this metric and then substitute it in the Einstein equation and see what are the allowed terms in that matrix so that it solves the Einstein equation. So this is how probably he got that solution. But this is the solution. He said that this solves the Einstein equation up to order epsilon square. So any RAB will come at order epsilon cube because the metric is written up to order epsilon square. So it is a solution of vacuum Einstein equation. And of course, since we are discussing about the incompressible Navier-Stokes equation, one always have this condition. Del A VA is order epsilon cube. So before that, everything is 0. So up to order epsilon square, del A VA is 0. So now you take a cutoff surface on the for that solution, which is at R equals to RC. Now, if you look at this metric at R equals to RC, the metric is simply this Rindler part. So the hypersurface is always Rindler kind of thing. And of course, the whole bulk solution is metric is always curved. If you look at the hypersurface, that is flat. But for the whole bulk solution, it is curved. Now come to the point how to get the Navier-Stokes equation from this solution. So then he said that, okay, since I want to assign my fluid on the hypersurface, I will look at the ADF decomposition of the Einstein's equations. We know that in ADF decomposition, Einstein equation have 3 parts, 2 constant parts and 1 is the dynamical part. So there are 2 constants, one is the momentum constant, which is this one. This T mu is your Brown-York stress tensor, and the other is the Hamiltonian constant. And other equation is the dynamical equation, which actually tell you that how the hypersurface evolves along the radial direction, because my hypersurface is at R equals to RC. But since you want to assign the fluid on the hypersurface, we look at these 2 constant equations because they are satisfied on the hypersurface. So then what he did is he took this momentum constant equation and calculated the T mu for this metric. And then what he found that at epsilon square order of that equation, it is del A VA equals to 0. And at epsilon Q order, it is not 0. If you say that it has to be 0, then we will get incompressible Navier-Stokes kind of equation. So what we have a bulk solution up to epsilon square order. For that, the momentum constant Einstein equation give you the incompressibility condition at epsilon square order. And to satisfy that Einstein equation, one will have to have the Navier-Stokes equation, incompressible Navier-Stokes equation on the hypersurface at order epsilon q. And from here, one can identify that this eta, which is the viscosity coefficient, is identified as the location of the cutoff surface. So what we did is we found a solution, or the Strominger they found a solution, which is the solution of Einstein equation. And on the hypersurface, the Einstein equation, the constant Einstein equation, is the Navier-Stokes equation at the relevant order. So far, I said that this solution somehow you can understand in this way. You have the base metric, which is regular. Then at each order, you add your terms, what are allowed terms. Then you say that, okay, I want to satisfy my Einstein equation, so that some of the terms will get cancelled and you will get the solution. But later, compare a secondary scalar, they show that actually this solution can be constructed in a different way. You start with the Rindler metric, and then you give the Lorentz boost along any arbitrary direction, and also along with you give a scale transformation of the acceleration parameter of the Rindler metric. I did not mention here what are those transformations, but idea is you first give the Lorentz transformation along any arbitrary direction. It has one parameter. For any particular, it will induce one parameter, which is velocity, and then you give another scale transformation, which also introduce another parameter, which is like pressure. So they identified alpha as the pressure and the velocity as the fluid velocity. But these are all constants because Lorentz transformation, the velocity is constant. Then what they did is, after giving this transformation, they took this velocity and the pressure like quantity as a space-time dependent. It depends on x, capital A, as well as tau. And then they expanded this thing, taking this velocity is a very small parameter, and then they kept up to order epsilon square, and they found that this gives to our Strominger's bulk metric. So this is how they constructed. So they said that you can actually generate this metric by giving a Lorentz transformation followed by a scaling, and then you take all these parameters as space-time dependent. So this is what we have for cutoff surface approach till now. But before going to my approach, I want to comment two things. One is, if you look at this approach, one is actually doing, one is saying that the Einstein dynamics as if it's a fluid dynamics. So I will call it the on-cell approach in the sense that Einstein equation of motion has been treated as a fluid equation. And the dynamics of the fluid is represented by the gravitational constant. So now, my question is, okay, do you always necessary Einstein equation to represent this fluid gravity correspondence thing? Or something we can actually tell that, okay, probably we can avoid Einstein equation and say that I can still write my fluid equation by a metric, or I can represent my fluid equation by a metric. So this is the first question we addressed. The motivation for me is, if you go back the earlier approaches of gravity, So there people actually try to show that gravity can be represented by a scalar field. What is the idea? Idea is we know that if there is a relativistic free particle, the action is just m times integration d tau. The d tau is your proper time. Now if we say that okay, my particle is interacting with gravitational field whose potential is represented by this phi, then I have to write down in a Lorentz invariant way. So I take a scalar which is phi and write down my action like d tau times 1 plus phi. Then to construct this action, one has to consider the equivalence principle. What is that equivalence principle? We know that locally one can always have a inertial frame so that acceleration can be ignored there. So in a weak sense, under gravity, any particle moves with the same acceleration. It does not depend on the mass. So what we have to do that to construct this action, we have to write down the mass as the overall factor, so that if you find out the equation of motion by varying it, it does not appear in the equation of motion, which is given by this equation. So now you see that this equation does not depend on the mass of the particle, so it is consistent with the equivalence principle. And also it depends on the velocity. This is always happening for the relativistic thing. So what I found is that I have a particle which is interacting, suppose say gravitational potential, then I can write down the action in this way and also the equation of motion. This whole structure equivalently one can represent in a different way. I can say that interacting picture can be replaced by a free picture, but now the particle is not moving on the flat spacetime, rather moving on a curved spacetime. So what we did in this action, we consider that the particle is moving on a flat spacetime and interacting with gravity. Then the whole system I has replaced by a free particle moving in a curved spacetime, whose metric is given by this one. So if you look at this idea, the idea is you take your spacetime as curved. So you represent your spacetime by say non-trivial GAV. Before going to the next thing, I want to mention that in the weak field limit, this is identical to the Rindler frame. So the lesson we got from this analysis or this discussion is that the interaction can be inferred in non-trivial spacetime, and a free particle moving on this represents the same interaction picture. So this is the idea we will take here to construct the metric for the fluid gravity correspondence of Navier-Stokes equation. Now the question is, can you use the similar idea? A free fluid is moving on the cut-off hypersurface of a properly chosen bulk metric that can represent the Navier-Stokes fluid. We found that this is indeed possible. We wrote two papers on that. One for the look at the fluid from the rotating frame, that has been already published, and the another one look at the fluid from the rotating frame. Here I will just discuss the simplest one, rotating frame, and I will tell you how to do that. The idea is similar to again Strominger. So Strominger actually borrowed the idea of ADS safety. You have to take a background which is quantum mechanically thermal, so you have to take the Rindler as a background. And then Strominger, what he did, he found the metric by allowing the terms which are allowed by that scaling argument. Here also we do the same thing. We allow the terms in the metric or the corrections on the over the Rindler by that scaling argument. But now the interpretation of the fluid equation not by the Einstein equation, rather I will tell that the acceleration of a properly chosen fluid velocity variable VA, which is given by this one, I choose it in this way because if you look at it, does not have radial component, so that the whole velocity field is lying on the hypersurface. And you impose the condition, the acceleration of the velocity field on the hypersurface is 0. So as if a free fluid is moving on a non-trivial background. So what we did is we construct order by order over the Rindler metric, and then the construction will be restricted in such a way that if we satisfy this equation over the hypersurface, we should get Navier-Stokes equation. If it is clear, we propose the metric in this. If you look at this is the Rindler one. This is order epsilon q. Order epsilon and order epsilon square, we don't need that one. So what we did, we wrote the metric up to epsilon q and chose the coefficients in such a way that if it satisfies this equation, it will give you the Navier-Stokes equation. So if you look at this metric, is much more simpler than Strominger. Again, like Strominger, it is also flat on the timelike slice, and we took this velocity and pressure, they are function of tau and xa, but independent of r. This is similar to Strominger as well. Then if you expand this equation, here the free index is c, so c can take tau, r, and the transverse coordinates. If you expand this thing on that background, on this background, then what will happen is it is trivially satisfied up to order epsilon q for the free index c and tau. Sorry, c equals to tau and c equals to r. This we should have because the metric is written up to order epsilon q. So whatever the equation we are imposing, that has to be satisfied up to that order. We found that this is automatically satisfied up to order epsilon q for if you choose c equals to time as c equals to radial area. But if you choose c equals to the transverse coordinates, then we will find that up to epsilon order q it is satisfied except order epsilon square. So now we are saying that, okay, I want to satisfy this equation at all orders. So you impose that condition as this is equals to 0. Then we will get this kind of equation. Now if we say that, okay, I choose my coefficients as 2, then it will give you exactly the incompressible Navier-Stokes equation. So what we found is that under the satisfaction of this condition at order up to epsilon q, for this metric, we have to satisfy Navier-Stokes equation. Now, if you look at this is actually the incompressible Navier-Stokes equation. But where is the incompressibility condition then? In Strominger case, they found that one from the Einstein equation itself. At the epsilon square order, they got the incompressibility condition, and at epsilon q order, they got the Navier-Stokes equation. Here we got at epsilon q order the Navier-Stokes equation, but not the incompressibility condition. Then what we found is that if you impose the condition that the expansion parameter of the velocity vector, if you define in this way, and that has to satisfy up to order epsilon q. Why I am considering that one? Because we take a particular velocity vector that represents the velocity of the fluid. So if the fluid has to be incompressible, those velocity vectors should satisfy the incompressibility condition. So therefore, you impose the condition that it should satisfy the incompressibility condition defined by this theta parameter. If you ask the thing is that this will satisfy up to order epsilon q, then one will find that at epsilon square it gives del A VA. So to satisfy that one, we will have the incompressibility condition. So you are getting two things from different equations. One from the free particle motion kind of thing on the hypersurface. Another is from the incompressibility condition. So what we found is that, okay, we can actually represent the Navier-Stokes fluid as if it is freely moving on a non-trivial on the hypersurface of a non-trivial background. Now I want to spend some time to understand this non-trivial background. We started with the linear metric. Then what we found is that if we have a linear metric in this coordinate in this form, and if we give this type of transformation on that metric, I am actually getting that metric we have proposed. So it seems that if you have a linear metric, if you go to a new coordinates which are defined by this set of coordinates, our required metric is correct. So the metric has to be flat. So it is again different from Strominger. Strominger has the metric which is the bulk metric is not flat, but in our case it is flat because the linear metric is itself flat, and what the metric we are constructing is coming from the linear by a coordinate transformation. So it's completely trivial kind of metric. So my comments are like, what we found is that since it is trivial, it should solve Einstein equation trivially. Since our metric is written up to epsilon cube, it solves up to order epsilon to the power 4. So this is fine. Then the suggestive analogy, what we are trying to say is that the viscous incompressible fluid residing on the flat space is essentially equivalent to a free fluid residing on the hypersurface of flat space-time, but in a different coordinate system defined by a unique choice of metric. So we have a flat metric, but we are looking at that thing from a different coordinates. And if we look at the hypersurface of that, the free equation gives us the Navier-Stokes equation. So as if a free fluid is moving on the hypersurface of that trivial metric, look from a different coordinate system. My ambition is probably something like equivalence principle. In normal gravitational equivalence principle, we know that the acceleration can be mimicked, or the gravity can be mimicked. Gravity can be mimicked from the accelerated frame. Here, as if like the viscosity terms, all the forcing terms of the Navier-Stokes equation probably can be mimicked if you go to a non-trivial coordinate system from accelerated frame. So our approach is I will call it the manifold approach, because all the fluid properties are encoded in the metric, the manifold. So I call it as a geometrical description, whereas the Strominger's approach I will call it as a dynamical approach, because it depends on the Einstein equation. We actually extended this approach for the rotating fluid as well, but I will not explain that one, just a mention. And what we found is that in this analysis, we never used any information of Einstein equation. So in that sense, I call it the off-cell approach. So we don't know, actually we don't require that metric has to be a solution of Einstein equation. It can be solution of any field equation. But the main thing is that the free fluid, as if moving on that particular background, is like a Navier-Stokes fluid. Now, what are the possible prospects of this approach? Don't take all these prospects as a very concrete one. It is just, we are actually extrapolating various things, but I want to just mention what are those. One thing is that if you look at the fluid dynamic or fluid dynamic paradigm itself, people are still struggling to find a proper action principle for the fluid equation. There are some approaches, but there are some problems in that approach, or there are some restrictions out there. So what we found that probably, since we are saying that fluid is lying on the hypersurface, probably from our metric we can construct an action for the fluid itself. It's like you write down your action as root over of GAV dxa dx, like what we always find the geodesic equation. I'm not sure that, but I am just hoping it may give some light to understand the action of the fluid. Another thing is that, as I say, it's an off-cell approach because I don't need the Einstein equation. So, if there is any quantum description of the fluid itself, then the quantum description should not be now encoded in the gravity. Whereas if you look at Strominger approach, he wrote the Einstein equation as a fluid equation. So if there is a quantum mechanics of the fluid side, then the quantum approach, to get the quantum approach from the quantum sense of the from the Strominger's approach, we have to quantize the gravity itself. But we are actually can bypass that one from our approach, because we are saying that the free fluid is flowing on a non-trivial background. So therefore, only you have to quantize the fluid on that background. So the quantum fluid on the flat Navier-Stokes equation is similar to the free fluid, quantization of the free fluid on the new background. So you don't have to quantize the gravity. Another thing is that it is the extrapolation of the earlier comment that here probably we can get some knowledge of microscopic description of gravity by knowing the microscopic description of the fluid itself, because we don't have to quantize the gravity itself. And this optional approach, why it is important? Because you already know that if there is any arbitrary null surface which may not be solution of a particular Einstein equation, one can encode temperature, entropy, everything on that. So it is some kind quote unquote optional kind of description, thermodynamic description of null surface. So since in gravity you have a null surface, you have temperature, entropy, everything, probably in fluid gravity correspondence also you should have that kind of thing. So you need a optional analysis for that. So our approach is in that direction. And another aspect one has to consider, if there are any higher order connections to Navier-Stokes equation, how to include in our approach. That is how to define a metric so that it include the higher order corrections to the Navier-Stokes equation. What does mean higher order corrections? If you look at the Navier-Stokes equation, let me go to the initial slide. Okay. So this Navier-Stokes equation is scale invariant up to order epsilon cube. The higher order correction means I can add epsilon to the power 4, epsilon to the power 6, all actually one can add odd order terms like epsilon to the power 5, epsilon to the power 7 to these things. And one can again to find out the metric for that. For Strominger approach, these people they already did that thing, but we don't know how to do that in our approach. We are trying to do that one. Hopefully we will do that. So the underlying understanding for our case is that you can represent your Navier-Stokes fluid as a free fluid on the hypersurface of a flat background, but look from a different coordinate system. So this ends my talk. These are the useful references. Based on this, to prepare my talk, and there are other references also. One can find out from these references. So thank you for your kind attention. Hello, I cannot hear.
Yeah, anyone who have questions can please ask Bibhas and let us thank him once again for such a nice talk. Yeah, any questions from the audience?
Am I audible? I have a question.
Yes, sir.
Shumantu, am I audible?
Yes.
Bibhas, am I audible?
Yes, sir, you are audible.
Oh, very good. Yeah, I have a couple of questions. First of all, I did not quite understand what you're trying to do in terms of the physics, because, in astrophysics, for instance, people work with both the Einstein equation and the Navier-Stokes equation, and there are numerical solutions available which give reliable astrophysical data, which also check out with experiment. So I'm trying to get solutions or map solutions of the Einstein's equation in some coordinate system to some aspect of the Navier-Stokes. I could not understand the motivation. That is the first question. What is the real motivation?
Let me give the answer to your first question.
Okay, so
yeah. So thing is that if you look astrophysics, we are treating these two equations differently. We are treating the gravity as a background and there is a Navier-Stokes. Here we are not doing that. What we are trying to, if there is a gravity dual of that Navier-Stokes equation, can we represent the Navier-Stokes equation as a gravitational system? This is our motivation. Now, why there is this motivation? As you said, all the solutions are numerically possible. There is no. So these two equations, if there is a question, if at all exact solution of Navier-Stokes equation exists or not, this is a very famous question or a problem exists in mathematics. So here we are trying to understand both the theory by giving a connection between them. One is the fluid side, another is the gravity side. And what we are trying to do, let us make a bridge between the gravity side and the fluid side. I am not taking them independently. I am saying that this gravitational equation on this background similar to your Navier-Stokes equation. So what we find, either you understand the gravity side properly for that background to understand Navier-Stokes equation, or to understand the gravity side, you try to understand the fluid side. So this is completely different what you said, because they are treating gravity and the background and the Navier-Stokes completely differently. It is like something is flowing under the gravitational background. Here we are saying that probably these two equations can be dual to each other for a properly choice of gravitational background.
Okay.
Sorry. Once again, I'm troubled with the physics. So sorry, Bibhas, because you see, I don't understand what the problem is. You see, because you did not apply your map to any specific physical situation. You did not say that, look, here I had, in the usual description, Navier-Stokes equation, I had viscosity. So take a viscous fluid like oil, and now if you do your mapping into this other coordinate system in a flat background, then I have some very nice physics coming out without having to deal with viscosity. You didn't discuss that at all.
No, I have viscosity. If you look at this equation, let us go to the incompressible Navier-Stokes equation. It's a viscous Navier-Stokes equation. It is viscosity, which is this one. So this eta is the viscosity of.
Yes, I'm not talking about the equations. I'm talking about the application of your map. Do you have any physical situation where you have applied it? Not to some space-time like Windler. I mean, that people know.
That's what I'm saying. It is not that you have two systems. One is the fluid system and the gravity system. It is not that. What I have two sides. One is the gravity side, another is the fluid side. I am connecting the gravity side with the fluid side. So it is not like a physical system, you have fluid flowing on a particular background. It is not like that. What I am saying, I have a fluid equation. That fluid equation also can be written as a gravitational equation. It's a one-to mathematical map between one equation with the other equation.
Okay, one last question I had is about the application of the ADN constraints. So the ADN constraints apply on a space-like surface. Now, did you apply it? I mean, I probably heard you wrong, that your hypersurface is timelike, but then you cannot apply these constraints. These are Hamiltonian constraints, which are valid on a space-like surface, right?
No, not necessarily. If you look at the ADN composition, initially it takes key constant surface, so it's a space-like surface. But also you can write down the same equation if you consider any, say, R constant or time-like surface. So it is not through that these equations are valid only for T constant hypersurface. You can take any timelike hypersurface also, you can write down that equations.
Sorry, I'm very confused by this statement because when you say that, you see, any Hamiltonian description is valid on a space-like surface. That's what you mean by Hamiltonian, right? And take quantum mechanics, for instance, right? When you write down the Hamiltonian, it's valid only on a time constant surface. So when you say that you apply it to any old surface you want, I don't understand it. You see, you have these spatial slicing, you foliate the space-time into space-like surfaces, and then the relationship between one space-like surface to another is described by the Hamiltonian constraint. So when you say you apply the momentum constraint, I don't understand. It's on a space-like surface, right?
No, what I am trying to say is that your time-like surface, on the time-like surface you have constraint, and the time-like surface, when you are saying it evolves, it evolves by the evolution equation which I did not write here. Those are not constant equations, those are the dynamical equations. So how that time-like surface is evolving, that is encoded in the dynamical equation. But these are constant equations.
No, look, in gravity, this is all you have. You can describe them in terms of lapse and shift as the Lagrange multipliers, but if you take pure gravity is just constraints. The Hamiltonian is just a sum of constraints, right? And these are constraints on a space-like hypersurface. That's exactly the Hamiltonian.
I understand your question, but you see, these actually.
Sorry, it's my problem, perhaps.
No, not your problem. I also was confused initially. This is actually the approach by the Strominger. This I stated along with the Strominger approach, but if you look at my approach, it's completely different. I did not use any kind of constant or Einstein equation. So my equation is this one.
Bibhas, I think if you don't call it a Hamiltonian constraint, just call the projection of the Einstein's equation on a time-like hypersurface, that solves Partho's problem. We should not call that as a...
yes, you are right. That nomenclature is fine, but Strominger somehow he used that nomenclature. That's why.
No, because if you say it a constraint, then obviously you mean it a general ADM decomposition, where then your surface has to be space-like. So you can't call it a constraint equation. This is just a projection of the Einstein's equation.
Projected Einstein equation on the hypersurface.
So can I ask a few questions?
Yes. Absolutely.
Yeah. So I have first a general question. For example, I can have, so do you feel that, or even in the Strominger approach, the idea is that given a solution of Navier-Stokes equation in a form of the velocity vector and pressure profile, this is a general solution of the Navier-Stokes equation, I can construct order by order a solution of Einstein's equation. That is the main idea of the Strominger's construction.
Yes.
Now, does it mean that every solution of Navier-Stokes equation I can convert into a solution of Einstein's equation? Because that is the disaster if that happens. Navier-Stokes unstable solutions. Most of the solutions of Navier-Stokes equations are unstable. In fact, it's an open problem that whether you can have a globally valid stable solution of the Navier-Stokes equation.
That's true.
Then it makes no sense. There will be a very few, maybe a set of measured zero solutions, which will be mapped into solutions of Einstein's equation.
Right.
What do we learn from it?
Okay, so let me answer this question. What I understood from Strominger's paper. If you look at Strominger's paper, at the end, he suggested two more matrices. Those are also solution of Einstein equations, and that also gives the Navier-Stokes equation, but with a different sign of viscosity coefficient. But what the problem of that metric is, it has a singular logarithmic singularity at infinity. So therefore he said that okay, since it has some problem, it is not finding the space-time properly at each point, probably we can ignore those solutions. So I cannot tell anything more above that. But his idea is, if you find other solutions, probably they can give you this Navier-Stokes equation. But one has to also check if the spacetime is properly defined at its spacetime point or not.
Okay, so let me ask you a very math question. If you go to your choice of the velocity field and the metric, when you construct you're right.
My approach. Okay. Yes. This is the
Yeah.
metric.
So what proposed metric is a choice, right?
Yes, this is choice.
What motivates this choice?
Okay. If you look at the Ringler part, if you start with the Ringler one only, and if you write down this equation for the Ringler case, this equation, it is like Euler equation.
Which one is Euler equation?
If you just take Ringler thing, not exactly Euler, because the pressure term is not there.
No, what I mean to say is that suppose instead of Navier-Stokes equation, I give you some other equation.
Okay.
You can always choose a metric for which this is like.
Yes, that's
So
it.
it feels like tautological. I give you an equation which is a some corrections to Navier-Stokes equation. You can always find the metric for which your equation, that gamma projection, will give you that equation back. It's a scalar equation, it's always possible. So
Yes,
there
that's
is
true.
tautology, right?
So what I am saying is that for a given equation, you can construct a metric. This is what you are saying, right?
So I don't know. What you are saying is that I give you any equation, even if it is not a Navier-Stokes equation, I can obtain it from any condition by choosing any metric.
Now, one thing is that you have to satisfy the scaling argument.
Well,
first of
scaling
all,
argument. What is the scaling argument?
That the incompressible Navier-Stokes equation has a set of solutions which are connected by a scaling.
But is it not obvious? It depends. It represents a continuous system.
Yes.
Is it not obvious? Because it doesn't see a molecule. There is no scale in the problem.
Right.
So what I mean to say is that suppose I start instead of Navier-Stokes equation, suppose I add another term to it. Now I add another term to your metric. I will continue to get the same equation.
Exactly. That is also true for Strominger as well.
No, Strominger is different. Strominger shows.
Not different. We check that one. Check that one. We check one thing. Let me say why I am saying it is also true for Strominger. If you look at the Strominger metric, you can add term which is like.
No. This is a solution of Einstein's equation, order by order constructed.
It is the solution of Einstein equation.
Which is
order the solution of vacuum Einstein equation.
Yeah.
If you say that I have a metric which is not vacuum solution, with some matter is there. You can define a different metric.
Then you have to solve it automatically.
Yes. Actually, we found another solution. We have in this paper.
The Strominger motivation is. So you are saying that there is what I am describing is correct, right?
Yes. If you one thing is that if you have a given equation like say Navier-Stokes equation, and if you know that there is a symmetry of that, like their scaling symmetry is there, use that symmetry and you can define a metric for that.
Okay, correct. So if you go to the last slide where you talk about every null surface have a thermodynamic interpretation.
Yes.
So I always wondered about it. Suppose I have a contracting null surface, light rays contracting. Its area is decreasing.
Yes.
How can it have a thermodynamic interpretation? The violate second law.
Actually, what I should say is that for the null surface, till now the existing literature, they actually say that there is like entropy kind of thing, temperature kind of thing there. And nobody has proved all those theorems if the area is increasing or temperature is constant on the surface.
But I'm giving you a counter example. The contracting light rays, the cross section of the area is decreasing.
Yes.
Okay. So the area is decreasing. It cannot have a, if you believe that the area is entropic, then it cannot have a thermodynamic interpretation.
I actually I agree with you, but what I'm saying that in literature there is some this thing is existing, but the thing is that nobody has proved that if those things are actually possible or not from the perspective of basic theorems.
Because why I'm telling you, the second law is not only a property of null surface, it's a property also comes from the global properties.
Right.
To prove second law, you have to use global properties of the event horizon. Unless you are using it like local horizon, where things can be done by local properties. But for event horizon, you have to use global properties. Okay, so it's not like any null surface. It's a very special null. Okay, I think
Yes, that's in that sense.
Yeah, I think this sort of mostly comes from the fact that you can write it in a thermodynamic form. So whenever someone says that null surface has thermodynamic structure, as far as I understand, the way they try to comprehend is that you can write down an equation like A is equal to dq plus dp. But whether second law is valid or not is, as you said, there can be situations where it is counterintuitive. But it's mostly like you can write it like a first law. That's what
I understand.
Yes.
Thank you. Thank you, Vibhas. Thank you.
Okay. Are there other questions from the audience?
I have a question. Stephen Watson from Glasgow, Scotland. So two questions. In this correspondence, is there a natural notion of turbulence that you can transfer over to this gravitational context? And
We are
also
actually
to come
just,
to
let me
Majunder's.
answer the first question. Let me answer the
Okay.
first question. Then we'll come to your second question. Actually, we are trying to understand the turbulence. If it depends on the position of the timelike hypersurface, we are trying to understand that, and we don't have any definite answer for that. But we have an intuition is that probably the turbulent condition will be satisfied depending on the location of the hypersurface, the RC. The value of the RC will depends on the condition for turbulence. But we don't know the answer right now.
Okay, so my second, it's not so much a question, it's more perhaps an observation. So I think it was Professor Majumdar had asked about the physical context in which you could apply these geometric notions of this correspondence. So I was thinking of an example of studying Onsager's turbulence hypothesis, and there's work by Laszlo Shekelhidi and Camilo Delelis using something called convex integration, which forms this kind of bridge between differential geometry and turbulence. So I just sort of highlight that. If you're not aware of it, it's something perhaps
Yes,
interesting.
I am not aware of that.
Yeah, so Camilo Delelis and Laszlo Shekelhidi. So I can maybe type that into the chat box.
Yeah. Yes, sure.
Sure. Thank you.
Thank you, Stephen, for the comment.
Yeah, so thank you very much. Any other questions? Okay, so I guess we are at around 5 o'clock, and we must all thank Bibhas for such a nice presentation. So hopefully we'll have you once again here. Next week, thank you very much, Bibhas, for coming.
Yeah. Thank you all.
Yes. So next week we have Debojyoti Shotkar from IIT Bhopal, and he will talk about some ADS